A strategic game is a rigorous mathematical model describing interactive decision-making, where actors make simultaneous choices, attempting to lock into a stable, synchronized outcome. We define this system using three formal primitives. We need a finite set of players, the specific actions available to them, and their preference relations over the possible outcomes. Once we have these parameters, we can calculate a Nash equilibrium. This represents a steady state in the system, a condition where every player holds perfectly correct expectations about the behavior of all others and acts optimally based on those expectations. This model encounters a mathematical ceiling. When we restrict players to strictly deterministic choices, many competitive environments fail to reach a resting state. To preserve the equilibrium concept, we must expand the mathematical primitives. We will start by translating discrete actions into continuous probability spaces, and then advance further, restructuring the shared information architecture itself. Nash equilibrium is not a behavioral process of trial and error. It is a strict mathematical condition of systemic stability. And for the model to hold analytical value, we must be able to guarantee that this stability exists. A pure strategy Nash equilibrium requires a specific mathematical condition. Given the optimal actions of everyone else, no single player can profitably deviate. The action chosen must sit perfectly within their best response function. We can test this condition using a classic coordination model, the Bach or Stravinsky game. Two players have a discrete set of actions, choosing either a Bach concert or a Stravinsky concert, and they want to coordinate their choices. Looking at this matrix, we find two stable coordinate points, both players choosing Bach or both choosing Stravinsky. At either of these nodes, deviating unilaterally lowers a player's payoff. The equilibrium holds. Consider a strictly competitive zero-sum game like matching pennies. Players choose heads or tails. One wins if they match, the other if they differ. Because interests oppose, the deviation condition cannot settle. One chooses, the other counters. The cycle loops infinitely. Relying on strictly discrete action sets fails to guarantee the existence of a fixed point across all game types. To achieve stability in strictly competitive environments, the mathematical space defining the game requires a structural expansion. We implement this expansion through the mixed extension of a game. Instead of selecting from a discrete list of actions, a player maps their choices onto a continuous probability simplex. By mapping actions to probabilities, the expected payoff functions become linear, continuous variables. This chart displays the continuous best response functions for the Bach or Stravinsky game we looked at earlier. We are now plotting the continuous probabilities of choosing Bach for both player 1 and player 2. Player 1's optimal response is represented by the dashed line. It shifts sharply across the axis depending on the exact probability that player 2 chooses Bach. Player 2's optimal response, the solid line, behaves identically, but charted against player 1's distribution. The functions cross at exactly 3 points. 2 sit in the corners at absolute probability values, representing our pure strategy equilibria. The third rests in the interior, mapping a mixed strategy equilibrium where probabilities intersect at 2/3 and 1/3. To hold this interior position, a stringent mathematical condition applies. A player is only willing to randomize their actions if their expected payoffs render them strictly indifferent between every available choice. Because the probability space forms a compact, convex subset, Kakutani's fixed point theorem mathematically guarantees that at least one such intersection will always exist in any finite game. Using continuous probability resolves the non-existence problem on paper, but it introduces a behavioral paradox, asking human actors to carefully randomize decisions when they have absolutely no incentive to prefer one option over another. If a mixed equilibrium requires strict indifference, there is no logical reason for a rational actor to deliberately calibrate a mental coin toss to yield exact probability distributions. In 1973, economist John Harsanyi proposed a theoretical pivot. He argued that mixed strategies do not represent deliberate conscious randomization by the players at all. Harsanyi redefined the scenario as a Bayesian game. He injected infinitesimal, private random variations, denoted as epsilon, into the player's expected payoffs. These invisible, unmodeled factors, a slight change in mood, a minor distraction,
shift the exact thresholds of choice. Given these microscopic shifts, each player makes a strict deterministic choice. The Sawney's purification theorem proves that as the size of these perturbations approaches zero, the aggregate sum of these strictly optimal pure strategies perfectly mirrors the exact probability distribution calculated in the mixed strategy. Ultimately, the system achieves a state of macroscopic stability as an elegant, emergent property of these chaotic, deterministic microfactors. A mixed probability is simply an outside observer's steady-state frequency distribution. It records the aggregate result of players reacting deterministically to private variables. Both pure and mixed Nash equilibria operate under a rigid, often hidden constraint. They assume player randomization is perfectly independent. We can expand the game space further by removing that constraint, defining a correlated equilibrium. Here, we integrate a shared objective probability space, represented as states x, y, and z, each occurring a third of the time. The players receive signals from this shared space, filtered through subjective information partitions. Player 1 can definitively observe if state x occurs, but cannot distinguish between states y and z. Player 2 possesses an overlapping but distinct partition. They cannot distinguish x from y, but can definitively identify state z. The optimization mechanic shifts entirely. Players select their actions mathematically conditioned on their opponent's incomplete knowledge of the shared signal. By anchoring their strategies to these correlated signals, the actors establish a stable equilibrium that secures a payoff profile of 5-5. This chart maps the game's overall payoff space, plotting the exact coordinates for every pure strategy combination available to the players. If we draw lines connecting the pure Nash payoff coordinates, we establish a bounded polygon. The shaded area within is the convex hull, defining the strict mathematical limits of independent play. Plotting the new 5-5 payoff reveals an anomaly. The correlated equilibrium exists entirely outside the convex hull. Introducing shared, partially opaque signals allows complex systems to stabilize at optimal payoffs that are mathematically impossible to reach when actors operate in isolated independence. We began with a model restricted to discrete actions, expanded the boundaries into continuous independent probabilities, and finally encompassed shared information architectures. Solving the problem of non-existence in game theory required abandoning the narrow view that a strategic interaction is merely a matrix of physical actions. Ultimately, the true steady state of a complex system is a stabilized profile of beliefs, a fully locked topology of shared information. By expanding formal primitives to include continuous probabilities and shared signals, we account for the stability observed in highly complex strategic environments.